So let's look at the general case. Let A be a square matrix of order n with row entries. There are n factorial elementary products. Of the form a sub 1, j sub 1 times a sub 2, j sub 2, and so on through a sub n, j sub n, where j sub I is an element in the set of consecutive integers from 1 to n, and j sub I is not equal to j sub k for any I or k in the range from 1 to n. Now notice in this form that the ith factor comes from the ith row of the matrix A. So recall that a permutation of the subset of consecutive integers from 1 to n is a bijection mapping this set onto itself. We can think of such a permutation as an arrangement of these integers in some order without omissions or repetitions. So notice that in an elementary product, a sub 1, j sub 1 times a sub 2, j sub 2, and so on through a sub n, j sub n of the entries of a square matrix A of order n, j sub 1, j sub 2, and so on through j sub n is a permutation of the set of consecutive integers from 1 to n. So no definition. An inversion occurs in a permutation j sub 1, j sub 2, and so on through j sub n of the set of consecutive integers from 1 to n whenever a larger integer precedes a smaller one the permutation is even if the total number of inversions is an even integer, and is odd if the total number of inversions is an odd integer. So let's look at an example. 2, 4, 6, 1, 3, 5 is the permutation which we'll call sigma, mapping 1 to 2, 2 to 4, 3 to 6, 4 to 1, 5 to 3, and 6 to 5. In cyclic notation, this is the product of cycles 1, 2, 4, and 3, 6, 5. Now, as this permutation has 0 cycles of even length, we know that the permutation is even. Let's now compare this to the total number of inversions. The integer 2 precedes the integer 1. The integer 4 precedes 1 and 3. And the integer 6 precedes 1, 3, and 5. There are 6 total inversions. And so the permutation is even. So new definition: a signed elementary product of the entries of a square matrix which we'll call A, is an elementary product multiplied by positive 1 if the permutation j sub 1, j sub 2, and so on through j sub n is even, and multiplied by negative 1 if the permutation is odd. So next we will define a symbol which will simplify notation. The Levi-Civita or permutation symbol is given by epsilon sub j sub 1, j sub 2, and so on through j sub n is equal to positive 1 if j sub 1, j sub 2, and so on through j sub n is an even permutation of the set of consecutive integers from 1 to n, and is equal to negative 1 if j sub 1, j sub 2, and so on through j sub n is an odd permutation of the set of consecutive integers from 1 to n, and is equal to 0 if j sub I is equal to j sub k for any I or k in the range from 1 to n, so in the symmetries on 3 letters, the Levi-Civita symbol is given by epsilon sub I, j, k is equal to 1 if I, j, k is an even permutation of the integers 1, 2, and 3. It's equal to negative 1 if I, j, k is an odd permutation of the integers 1, 2, and 3, and is 0 if I is equal to j, j is equal to k, or k is equal to I. So notice we can use the formula epsilon sub I, j, k is equal to the product, the quantity I minus j times the quantity j minus k times the quantity k minus I, all divided by 2. Notice that if I is equal to j, j is equal to k, or k is equal to I, then the numerator is 0. Otherwise, the numerator is a positive 2 or a negative 2. So when we divide by 2, we have positive 1 or negative 1. And in the set of symmetries on 2 letters, the Levi-Civita symbol is given by epsilon sub I, j is equal to 1 if I, j is the permutation 1, 2, negative 1 if I, j is the permutation 2, 1, and 0 if I is equal to j. So let's look at an example using the Levi-Civita symbol in a computation. epsilon sub ij times a sub I times b sub j is a sum of products. Since the index I is repeated and the index j is repeated, by the Einstein summation convention, we have the sum from I equals 1 to 2 of the sum from j equals 1 to 2 of the product, epsilon sub ij times a sub I times b sub j. If we expand this sum for all values of the index j, we have the sum from I equals 1 to 2 of the sum of products, epsilon sub I1, a sub I, b sub 1, plus epsilon sub I2, a sub I, b sub 2. If we now expand this sum for all values of the index I, we have epsilon sub 1, 1, a sub 1, b sub 1, plus epsilon sub 1, 2, a sub 1, b sub 2, plus epsilon sub 2, 1, a sub 1, b sub 1, correction, a sub 2, b sub 1, plus epsilon sub 2, 2, a sub 2, b sub 2. Now, since the indices are equal in the term epsilon sub 1, 1 and epsilon sub 2, 2, the value of the Levi-Civita symbol is 0, and so these terms are 0. 1, 2 is an even permutation, while 2, 1 is an odd permutation, and so we have a sub 1, b sub 2 minus a sub 2 times b sub 1. So new definition. Let A be a square matrix of order n with real entries. The determinant of the matrix A, which is denoted det A, is the sum of all signed elementary products of the entries of the matrix A. That is, the determinant of A is epsilon sub j sub 1, j sub 2, and so on through j sub n, times a sub 1, j sub 1, a sub 2, j sub 2, and so on through a sub n, j sub n. So let's look at an example. Let A be the 2 by 2 matrix with rows A11, A12, A21, A22. Then the determinant of A is epsilon sub ij, a sub 1I times a sub 2j. Now we will only consider the Levi-Civita symbols where the indices I and j are not equal, and so there are two permutations, 1, 2 and 2, 1. So this is epsilon sub 1, 2, a sub 1, 1 times a sub 2, 2, plus epsilon sub 2, 1, a sub 1, 2 times a sub 2, 1. The permutation 1, 2 is even, while the permutation 2, 1 is odd, and so this is a sub 1, 1 times a sub 2, 2 minus a sub 1, 2 times a sub 2, 1. Notice that this is the product of the entries on the main diagonal minus the product of the entries on the anti-diagonal. So let's look at a concrete example. Let A be the 2 by 2 matrix with rows -3, -1, 5, 2. Then the determinant of A is negative 3 times 2 minus negative 1 times 5. So this is negative 6 plus 5, or negative 1. So as an exercise, let B be the 3 by 3 matrix with rows B11, B12, B13, B21, B22, B23, B31, B32, B33. Find the determinant of the matrix B. Okay, so we will end here for today. Next time we will continue our study of determinants, and in particular look at their relation to inverses of square matrices. So I hope you have enjoyed the 10th lecture. Thanks for watching.